All right, welcome everyone to today's seminar. Today I'm happy to have Dr. Harry Arnold with us. He graduated from the University of Maryland in 2021, where he worked with Jim Drake and Mark Swisdak on super thermal electrons and macroscale magnetic reconnection. Since then, he's moved on to Johns Hopkins Applied Physics Laboratory, where he's currently working as a postdoc investigating particle and cell and magnetohydrodynamic simulations of the magnetotail and the magnetosphere. Today, I'm happy to have Harry here talking to us about his particle and cell simulations of the magnetotail and ion current sheets. So with that, if you would like to take it away, Harry.
All right, thank you. So I'm going to be presenting some work I've been doing with Misha Sitanov, looking at the PIC simulations of overstretched ion scale current sheets. And in particular, what we find, and I'll show this later, that Spitzer orbits are very important in these ion scale current sheets. And so this first picture here, this is a picture taken from that Spitzer 65 paper, just showing what the orbits look like. But you have your curved magnetic field like the magnetotail, and the protons and electrons gyrate around until they enter the current sheet, where they orbit around the normal component of the magnetic field, and their orbits often look something like this. So this is the Spitzer orbit, and we'll come back to this in the future. Let me move on. I skipped a slide. Okay, there we go. So I'm going to talk about reconnection and substorms just as an overview, although I imagine most people here have a pretty good understanding of this. We'll just gloss over some details. Then I'll talk about some data mining reconstructions that really inspired this work, and talk about observations of these overstretched thin current sheets, and in particular how isotropic force balance is not sufficient to explain them. Then I'll describe the new model, including the PIC simulation results, talk about how you get force balance with those Spitzer ions, and I'll conclude with some new simulations that we've been doing where we've been forcing the thin current sheets with an electric field like the solar wind, and also including some BZ humps to try and make them unstable. So just as a reminder, magnetic reconnection. You start off with anti-parallel magnetic fields above and below a current sheet. They reconnect in the middle, and they convert magnetic energy into plasma energy. You get thermal heating, you get alphanic plasma outflows along the current sheet. Non-thermal particles can appear, and of course magnetic islands as well, or plasmoids as they're sometimes called. The current sheet in, especially in PIC simulations, that is often studied is some variant of the Harris sheet. And basically what is typically considered as an isotropic plasma. And with that, you end up with a magnetic field that looks like a tanch that goes across the current sheet. The current density and the density are sort of proportional to each other. And your distribution function is typically a Maxwellian of these, and a function of these invariants, the canonical momentum, the out of plane canonical momentum, and the energy of the particles. So that's yeah, right. So that gets you reconnection, and then there have been many studies. This is just one example where you can see some plasmoid formation in the simulation. Now let's just take a second and talk about substorms. Effectively, you can think of the Earth's magnetic field as a dipole, except of course it interacts with the solar wind, so it becomes compressed on the day side and it stretches out quite a lot on the night side. There's something called the Dungy cycle, which I imagine most people are familiar with, where effectively when on the day side, the solar wind interacts with the magnetosphere of the Earth, and you can get reconnection there. That reconnection creates this new field line that then gets swept to the night side, where it compresses the tail, and you get reconnection on the night side as well, causing these earthward flows that can be problematic. This is just a standard video of a substorm that I just pulled off the NASA website that I think illustrates all the points quite nicely. You start with the sun, you get your solar wind going towards the Earth. There we go. Now we have our magnetosphere, and you can see it's compressed on the day side, and when it interacts with the solar wind, it can compress and get these reconnected field lines that squish the night side until it reconnects there as well. And then, of course, this movie ends with the Northern Lights, which is just the perfect ending for a substorm. On the left, this is from a Wiltberger et al. 2015 simulation. And it really shows you the power that these global MHD simulations have, the ability to simulate so many crucial physics of these substorms. Just going to play it briefly one more time. But you see, the solar wind hits the magnetosphere, you get these nice compression in the magnetotail where you eventually get reconnection, and then you get all these bursty bulk flows towards the Earth. So these global simulations have a lot to offer us, of course. Next slide. Here we go. So substorms, brief disturbances of the Earth's magnetosphere that occur every few hours, and they are caused by this rapid reconfiguration of the Earth's magnetotail, where it's first stretched and then it dipolarizes after some sort of onset instability, which is likely reconnection, at least some of the time. You can detect them with ground-based magnetometers, and we get all these different geomagnetic indices. And of course, the northern lights or the aurora are a big part of what substorms, of how substorms affect the Earth. They can be quite strong and, of course, pose problems for both electric grids and satellites in orbiting space. All these good things. So now I want to talk about some new work, relatively new work here, called data mining reconstruction. So this is a work done by my colleagues Grant Stevens and Misha Sitnov. And what they're trying to do is recreate the magnetic field of the Earth for a given snapshot in time. The way they do this is they have a database of 10 million plus magnetometer measurements. And they put that, these are, I should say, spacecraft magnetometer measurements. And they put those in this 5-dimensional state space. So in the state space, we have the substorm index AL and its time derivative, or SML for supermag. And we have SimH or SMR and its time derivative as well. And then we have the solar wind electric field, kind of the driving force on the magnetosphere. And so when you put all these points in this 5D state space, you can then select, just say, the nearest 30,000 odd points or so to your moment of interest, right? So at any given point in time, you know where you exist in this 5-dimensional state space, and then you just grab the 30,000 points that are nearest to you. And then with that, you can fit a magnetic field model and recreate the Earth's magnetosphere. So this is an example down here. Each of these gray points is a virtual satellite that exists at the time of interest. And you can see that this is the equatorial plane, and there are many different contours of BZ, but in particular, you get this BZ equal to 0 contour. Now, what's particularly interesting about this is that this really shows you where the topology is changing in the magnetotail. So on the Earth side of this contour, you get an X line, and on the night side, you get an O line. And this can be more easily seen in the 3D reconstruction here. Again, you have the MMS observation that's located approximately here, and you can see a nice X line, and then this flux tube is centered around the O line. So that's how these reconstructions work, and they've seemed to be doing quite well. One aspect to these reconstructions, though, is that they use 2 different current sheets in the magnetotail. They use a thicker current sheet and a thin current sheet, which is required to be thinner than the thick current sheet. And what's interesting when they do this is pretty much for every substorm, what they see is during the growth phase, you get this buildup of the thin current sheet. And then during the expansion phase, the thin current sheet decays. And so you can see that that's this orange line here. This shows the thin current sheet and the current associated with it. And in each of the growth phases, you get this buildup of that current. And then in the expansion phase, it decays away. And that seems to be pretty ubiquitous in every substorm that they've looked at. I think they've seen this pattern. So this suggests that these thin current sheets can be playing a significant role in substorm dynamics. And I'll just briefly talk about this BZ hump that is not always seen, but is, it's a common feature of these substorms, both in the reconstructions and in situ observations. But you can get this BZ hump, where basically if you plot BZ as a function of distance in the tail, it starts increasing at a certain point. And that gives you a hump. And this appears to be a driver of the substorm onset. It can be unstable. And that leads to, the whole substorm dynamics and a redistribution of flux, where eventually you get more dipolar magnetic field closer to the Earth, as you might expect from a substorm. Okay. So this is just another example of this thin current sheet buildup. This is for a particular substorm, 2008. In the growth phase, that's these top three plots you see in the equatorial plane here, you have contours of BZ again, and you can quite clearly see that BZ hump I was just talking about. But if you look at the current sheet, you also see this thin current sheet that goes almost entirely across the magnetotail and is several RE, 5 RE in width, maybe a little bit more. So it's a big chunk. Excuse me. It's a big chunk of the current sheet of the current in the magnetotail, and you can also see it in the meridional plane as well. But then after the expansion phase, you can now see the BZ hump is pretty much gone, the thin current sheet is gone, and you're left with a more dipolar field. So once again, this thin current sheet, this may be playing a significant role in substorm dynamics. And finally, just a final note about these data mining reconstructions. You might be saying like, okay, all well and good, but how accurate are these data mining reconstructions really? And I think a very good illustration of the power of these reconstructions is in this comparison between data mining reconstructions with their X lines and O lines and MMS observations of ion diffusion regions. So these ion diffusion regions, they correspond to X lines and O lines, and they were really observed in situ by MMS. There's a list of 26 of them. And of that 26, data mining was able to successfully reconstruct 24 of them. So these are just 4 examples on the right here. Again, this is all the equatorial plane. You have contours of BZ equal to 0, as well as contours of BZ equal to 2. And then this green dot is where MMS observed an ion diffusion region, or IDR. And you can see it nicely matches up to either an X line, which is the earthward side, or an O line, the nightward side of these contours every time. And even the 2 events that were missed, there's some reasons for that I won't go into. But the point is that these reconstructions seem to be doing an excellent job of capturing the night side magnetosphere. So let's just talk a little bit about actual observations of these overstretched thin current sheets. So for one, the Runov et al. 2005 has this nice distribution histogram of the width of the current sheet as just depending on how many cases that they saw. And the point here is that H is the width of the current sheet, and this LCP, that's the upstream Larmor radius. So basically, to get an ion scale thin current sheet, you really want to be in one of these 2 left columns, certainly the left one, maybe also this middle one. And so you get, not all current sheets, of course, are these overstretched ion thin current sheets, but a significant fraction of them are. So they do exist, and there's a lot of them. And indeed, they can be up to 20 RE in length, quite long thin current sheets going into the tail. Now, the trouble with this 20 RE here is that if you just consider force balance with isotropic pressure, right? So, in a steady state system with no flows, quiet time, you can't achieve this 20 RE. You can go through some math, and effectively what you get is this ratio here. But if BZ over BX equals 20, which is a very reasonable answer, then that would give you a distance into the tail of 2 RE, assuming that it's an ion scale width. And that's just not nearly close enough. That's an order of magnitude shorter than what's actually observed. And so this suggests that you need something more than isotropic pressure to achieve the actual aspect ratio of these current sheets. And so one thinking has been, well, maybe it could be the electrons. If you have anisotropic electrons, that could then provide you with the remaining force balance. And so there you have this Artemiev et al. 2016 paper. And on the bottom right here, I'm showing the electron anisotropy as a function of Bx, which is basically to say distance from the current sheet. And what you see is when you're very close to the current sheet, you do have some slight electron anisotropy, but it's extremely small. And when you couple that anisotropy with the fact that the electron temperature is already much smaller than the ion temperature, it's really, really difficult to get those electrons to give you the appropriate force balance to get that 20 RE in length. And so another way of illustrating this is this other plot here. Here we have this ratio basically between the J cross B force and the grad P force, the pressure gradient force. That's this solid line. And then if you were to add the electron anisotropy to the pressure force, you get this dashed line. And you can see it brings it down. So if your J cross B force and your div P force are the same number, right? You get 1, and then you've got balance in your equation. And so by including the electron anisotropy, you get closer to 1, but you're still far off from 1. So electron anisotropy alone is not going to be enough. And even the electron anisotropy barely shifts it in the appropriate direction. So it's not the dominant player. You really need something else. Oops. Sorry. Let me just, okay, all right. This is the right slide. Okay, so electron anisotropy is no good, but I want to add to that a little bit, which is going back to this idea of X lines in the magnetotail. So data mining reconstruction was able to match observed X lines. But if you look at global MHD simulations, these simulations often show reconnection. So that's this blue line here, very close to the Earth. This is, 12, 13 RE away from the Earth. Similarly to this one down here, you get this X line very close to the Earth. These are two examples from these global simulations. However, in reality, these X lines are observed much further in the tail, 20 RE, certainly more than 15 RE, and they only ever get within 15 RE for very strong driving scenarios. But in both these cases, the driving was not very strong, and yet we still get X lines close in. And the thinking here is, if I just go back for a moment, if you don't have something besides isotropy, or I guess I should say, if you just have isotropy in your model, like MHD does, then you can easily end up with an aspect ratio of this, which gives you a very short current sheet in the tail. And that would lead to reconnection much closer in to the Earth. But that's not where it's observed. And so, do these thin current sheets give you the current further in the tail where reconnection actually occurs? And therefore, are they, how do I say this? Are they playing a big role in reality that is not being captured in these MHD simulations? So this is a question that we're interested in. Okay, so finally, I want to talk about the observations of ion anisotropy here. So as I said before, with isotropic force balance, that's not enough. You can kind of see exactly how the anisotropy is playing a role here. If you just look at your force balance equation, you get J cross B on the right, you got div P on the left. This is sort of your isotropic component. But then you have these off-diagonal components. Oops, sorry. You have these off-diagonal components, and these come from the anisotropy. And you can see that quite clearly from this equation down here. If P parallel minus P perp is non-zero, then you will end up with some off-diagonal component, and that can contribute to your force balance and balance your J cross B and result in thin current sheets. And this image here, this is from this Yushkov et al. Paper. And basically what they did was they plotted the anisotropy for ions in blue and electrons in red for many different events as a function of the thinning. So BZ is the x-axis here. And you can imagine as your current sheet thins, you're going to go from the right side of this plot to the left side. And when you do that, you'll notice that for pretty much every single one of these at the leftmost side, you end up with a little bit of positive ion anisotropy, such that T parallel is greater than T perp. So we know that there is some electron anisotropy, but electrons aren't going to be enough. And we know that there are some ion anisotropy. So the question now is, well, are ions enough? So let's talk about that a little. So last year, Misha Sitnov and I came up with this approximate initial condition for this equilibrium involving these overstretched thin current sheets. And the key here is that our distribution function is a function of the out-of-plane canonical momentum, just like the Harris current sheet, and a function of the energy, again, like Harris. But now we also have this function of the quasi-adiabatic invariant, which is approximately conserved for Speiser orbits. So we're guessing right out the gate that Speiser ions may be playing an important role here. But when you put that into your distribution function, of course, all of your equilibrium equations are going to change to some extent. And what we are interested in is a nice analytical expression that we can use. But of course, we have to make some assumptions. So we make these three assumptions up here. We assume small anisotropy. So we do have anisotropic ions, but it's small. We have this small embedding factor, which controls effectively the thickness of the thicker current sheet that our thin current sheet is embedded in. And in the Harris equilibrium, this is effectively the drift speed of the ions in the out-of-plane direction. And finally, we have this stretching parameter, which basically, because we're interested in a magnetotail-like geometry, we start off with some BZ, and this controls just how strong that initial BZ is, which stretches your magnetotail field lines. And so you do a ton of math and you use these small parameters and make those assumptions, and you end up with this equation for the magnetic field right here. And what you'll notice is if you set delta 1 to 0, and so you say we have isotropy, then this term becomes 1, this term goes away, and you're left with B equals tanh, which is exactly what the Harris current sheet is. So when you get rid of our anisotropy, you recover the Harris current sheet, which is quite nice. And so on the right here, I've plotted various quantities. And this dotted line here, that is the Harris current sheet that is these quantities in the Harris current sheet as a function of zeta or Z. And then for various values of the anisotropy, we've plotted these other values. And something to note is that the current sheet very clearly has a thin current sheet right in the middle, and then this much thicker current sheet as you go to further out in Z. And in particular, the Harris current sheet, the density is proportional to the current. You can kind of see that in these two dashed lines here. But when you go to the thin current sheet, you no longer have that case. That's no longer true. And instead, you get this nice thin current sheet, and the density is still relatively unchanged. Okay, so these are the equations that we're using for our PIC simulations. And here is the result. So we use those equations to initialize our PIC simulation, and then we let our PIC simulation run. In this case, we ran it out to 60 ion cyclotron times, just to see if it is in fact stable or not. And it is. It appears to be perfectly stable. So here on the top, I've plotted the density, and in the next plane, I've plotted the current. And again, you can see that our current sheet is embedded inside of our thicker ion density sheet. And interestingly, the contours of our current overstretch the contours of the magnetic field lines, which is totally different from Harris, where the contours of current and the contours of the magnetic field match up. Here we overstretch it, and I'll show that in another plot later on. This is the local ion anisotropy. So in the dead center of the current sheet, we're anisotropic, but as you go upstream, we get this anisotropy, which in this case, I think is about 0.2 in the asymptotic limit. But we are agyrotropic in the current sheet, and this is actually an important role. And it's interesting as well, because if we are agyrotropic, then this, of course, furthers to suggest that MHD is going to be missing this kind of kinetic physics. But even you know, the CGL equations or anisotropic MHD, it won't capture this aspect, the fact that our ions are indeed agyrotropic. So that does make this difficult to capture in global simulations. And finally, this is that off-diagonal pressure component that is contributing to our force balance. Now, I don't know if this was clear from our equations, probably wasn't, but you can very easily argue from symmetry that our equations say that at the beginning, this term is zero, this off-diagonal pressure term is zero. So this that you're seeing here, this structure, this actually develops throughout the run, but it reaches an equilibrium, and it is quite small, but it's significant enough in the force balance, as we'll see in just a moment here. Okay, so let's talk about the force balance. Let's look at this plot first, these two comparison plots. The top one here, this is at t equals 0, and the bottom is at t equals 60 once we've reached equilibrium. And I'm plotting several different values here on each plot. So this solid black line, this is the J cross B force that we're trying to balance. So this is balancing this will give us a nice long thin current sheet, and that's what we want. The solid red line, this is the pressure, the contribution to force balance from the isotropic part of the ion pressure tensor. And the solid blue line is the same for the electrons. So if this were a Harris current sheet, you would just have the solid blue line and the solid red line, and that would be it. And that's what we have at this time. But in fact, we're not in force balance, right? The sum of the red and the blue line, which is basically this dashed black line here, does not equal the J cross B line. So this dot dash line here, this is J cross B minus the sum of the divergence of the pressure tensors. So if this line equals 0, then you're in equilibrium, but it's not 0 at the beginning of our simulation. But by the end of our simulation, it is 0. So why is that? Well, if you look at the electrons, you get this isotropic component in solid blue, and now you get the off-diagonal component in dashed blue. Those are both practically 0 in our simulation. But the dashed red line now, which was 0, has suddenly reached a value almost equal to the isotropic pressure component, the solid red line here. And this is that off-diagonal pressure component. And that is what gives you force balance. And so you can see this kind of evolve in time. If you look at the difference between J cross B and the divergence of the pressure tensors, which again, if this quantity is 0, you have equilibrium. If you look at the average of that between 20 and 60, as a function of time, you see it oscillates on some small time scale. But on a longer time scale, it decays to 0, and we get equilibrium. And this solid red line here, this is just an exponential to show you that the time constant to reach equilibrium is about 10 ion cyclotron times. Okay, so what's going on here? Well, this bottom left plot, this shows cuts based as a function of Bx. So again, think of this as being across the current sheet, up and down, sort of your Z direction. And we've plotted the current in black at t equals 0 and in green at t equals 60, and then the density orange at 0 and blue at 60 for two different values of x. So this is on the leftmost side of the box, this is in the center. But there's a couple of things I want to point out here. First, you easily see right out the gate that the density is not proportional to the current. So this is a point I've made a couple times, but in the Harris current sheet, density is proportional to current. In the overstretched thin current sheet, they are not the same. But because we're in equilibrium, you do see that between t equals 0 and t equals 60, they basically remain unchanged. The only thing that's really changing here is this off-diagonal pressure component to give you force balance. Everything else is roughly constant. And finally, the thin current sheet, which you can see is basically this much of the current sheet. This only reverses about half of B naught. So you imagine at the asymptotic limits of the box, Bx is basically, plus minus B naught. In the center of the box, it's 0. But if you look at the edge of the thin current sheet here, this gets you it reverses plus minus 1/2 B naught. Okay. So that's important, because if you try and look at this off-diagonal pressure component, and in particular the gradient of it, let me back up a couple slides. So we're interested in this off-diagonal pressure and the gradient of it to balance the J cross B force. So if we take this equation and we start plugging in values, we can P parallel minus P perp is about 0.1 in this case. We get J cross B over B squared. And so the question is, well, what is this B squared? And you might be tempted to say it's the true asymptotic value, but it's really just the asymptotic value according to the thin current sheet, which only reverses 1/2 of B naught. So that gets you this factor of 4, and you get the end result that your off-diagonal pressure component here that you get from ion anisotropy is responsible for about 40% of the J cross B force. The remaining 60% is due to the isotropic ion pressure. So the anisotropy here is doing a lot of heavy lifting, even though it's small, because this 1 over B squared factor is also small. I'm sorry, 1 over B squared is large. B squared factor is small. And actual observations suggest that it might even be larger than 1/2, maybe a quarter or a fifth or something like that. So now the next part here that I got interested in is actually looking at the particle distribution. So I took this red box here and I looked at the ion distribution inside of it, and I plotted that in this top left plot. So this is actually the log, but it's the distribution function. And you can see that it looks more or less the way you would expect a Maxwellian distribution to look. It's only slightly different. And that is, not terribly surprising, because of course we have these small parameters that make the difference between this current sheet and a Harris Maxwellian current sheet. But I took all these different green circles here, these rings between them, and I plotted various quantities. So this plot here, this shows the density as a function of this VR is what I'm calling it, but it's the radius of these green shells in VXVZ space. And then I did the same thing for the off-diagonal pressure contribution, right? So this bottom plot here, this shows the local contribution in phase space to this off-diagonal pressure component. And then this plot here, this shows that line through each of these shells as a function of VR. And if you look at the shell that contributes the most to this off-diagonal pressure component, that corresponds to this location in density. And you can immediately see that the ions that contribute the most to the off-diagonal pressure are actually superthermal ions. They are not the thermal ions. They're more energetic than that. And if you put some test particles at this location in phase space and just evolve them for a while to see what their orbits look like, you get these very clearly meandering orbits or figure-8 orbits, which are the two type of Spicer orbits that I talked about at the very beginning. These are Spicer ions that give you this off-diagonal pressure, and then that results in getting force balance for your thin current sheet. So this is the same, these two plots here are the same as these two plots, but with a critical difference. In these plots, I have completely integrated over Vy, and everything's just Vx and Vz. But in these plots, I split up that integral in Vy into 4 different parts. So we have this left tail, this, what am I calling it? The left standard deviation, the right standard deviation, and then the right tail. And I plotted it for density, and you can see that the density in each of these 4 areas in Vy are basically the same, or rather symmetrical, which is what you'd expect. But the dominant contribution to this off-diagonal pressure component, that comes from this negative Vy region here, this left standard deviation. So these particles contribute a lot more than these particles. And that actually those ions are these meandering ions. The figure of 8 ions are the ions that have some positive Vy. Those ions don't contribute as much to the off-diagonal pressure. It's the meandering ions that we care the most about. So this plot here, this just tries to give you a sense of what the different parameters can make the current sheet look like, and in particular, how it compares to the Harris current sheet. So on the top here, this is an overstretched ion scale thin current sheet. You can see that the contours of the current do overstretch the contours of the magnetic field lines. But these 2 plots on the bottom here, these are both Harris-like current sheets. So you can see the contours of the current match the field lines quite nicely. But let's look at the aspect ratio. So this middle one here, this tries to make the width of the current sheet at the left part of the box the same as the thin current sheet, but it is significantly shorter. You can see that very clearly. I mean, the thin current sheet basically goes across the whole box, whereas the Harris current sheet most certainly does not. The bottom plot tries to get the current sheet length in X to be the same as the thin current sheet, though you can see it doesn't do quite as good a job. And the left part of this box now, the thickness here is obviously much longer, much wider than the thin current sheet. So these thin current sheets do get you a more realistic aspect ratio. Now let's just talk about reconnection in these PICs in various simulations that have magnetotail geometry. And basically it boils down to 2 different ideas of a way to make this geometry unstable with reconnection. The first, which I think makes sort of the most simplistic amount of sense, is electron demagnetization. And the idea there is, you start off with some magnetotail-like geometry, and you just squeeze it with an electric field at the boundary conditions here, which represents the solar wind just squeezing your magnetotail until you reach electron scales, at which point, of course, your electrons are demagnetized, so you're going to reconnect. No real surprises here. You get a lot of plasmoids and reconnection, and you can reproduce a lot of features that are observed in reality. So this is, a possibility. The other one, which is a little weirder, is this ion demagnetization idea. Here, you don't have to squeeze the current sheet, so this can be more spontaneous. Instead, what you start off with is this accumulation of flux, or this BZ hump that I was talking about earlier. And it turns out, for various reasons, that this BZ hump is unstable. And so it will start moving earthward. And as it moves earthward, it sort of stretches out the field behind it with some sort of like flux starvation mechanism. And then that can effectively squeeze the magnetotail behind it enough until the electrons are demagnetized and you get reconnection. So this is ion demagnetization mediated reconnection. And both of these, there are observational evidence for both of these, and there are many simulations showing that these can truly destabilize this magnetotail configuration. So we started playing around with that in our new equilibrium. So this is just overstretched thin current sheet with forcing. So there's no BZ hump. It's just our standard equilibrium, but now we've applied this electric field. And indeed, we squeeze down to electron scales where we eventually reconnect. So you can see in these 2 plots here, I'm showing BZ, and you can see that it just reverses right here and we get, which must mean that we get reconnection. And this actually, before we even see that reconnection, we get this nice ion watershed. Basically, the forcing electric field squeezes the ions out, and that's going to drag on your field lines until you get reconnection deep in the tail, which is nice. And this is sort of consistent with what we would hope to see in terms of where reconnection takes place. And this bottom simulation here, this is very similar, although it also has a hump. But again, you get this reversal, and the hump is also moving earthward a little bit, as you might expect. So this simulation here is similar to the last one. Again, no hump, just forcing. But what I wanted to show is that you can see that although at late time, 120 ion cyclotron times, you get many different X lines here, you get one dominant X line. And you can see that it's the dominant X line because this is where the electric field penetrates the current sheet. And indeed, it gives you a reconnection rate of about 0.1, which is exactly what you would expect. So you get plasmoids, yes, but you get one dominant X line deep in the tail, and that primarily is doing the reconnection in this simulation. Okay, and then this last simulation here, we've decreased the forcing quite significantly, and we put in a BZ hump about halfway into the box, and we just, let it go to see what would happen. And of course, eventually you do get reconnection, which is as you'd expect. But what's particularly interesting about this simulation is that if you look at the hump at late time, you get an electric field that is noticeably larger than your driving field. So driving field is about 0.025. You can see that even on this color scale, which is minus 0.05 to 0.05, you're saturating. So the electric field here is larger than our driving field, which suggests that we do still have this BZ hump instability in the thin current sheet equilibrium. So we've yet to fully confirm this with just a BZ hump and no driving, but the fact that we're able to generate a larger electric field suggests that this instability does exist. Okay, so I'm basically done here. I just wanted to talk about a comparison that I've been looking at recently with some of my colleagues, which is looking at these MHD simulations in comparison to the data mining reconstruction. So on the bottom, you have your data mining reconstruction for a given point in time, and the top you have the MHD simulation. On the left, I'm showing various solar wind parameters as well as the geomagnetic indices. Let's see, we have SML, SMR. So you can see that, not really a storm at all. This is just another isolated substorm. And in fact, this point in time is before the substorm really kicks off. It's like right before. And what's interesting is how different these two images look. Basically, the MHD version of this substorm is showing that you get an X line too close to the Earth, as sometimes happens in MHD. But then tailward of that, you do get a nice thin current sheet. Now, of course, if you have an X line in reconnection, this isn't going to be a quiet like current sheet because you have alphanic outflows basically affecting things. But in the data mining reconstruction, you have your thin current sheet, and instead of getting reconnection anywhere, what you've really done is you've just stretched your field lines out so that it's less dipolar, and they're ready to sort of spring forward again as the substorm progresses. And so the thinking here that we have really just sort of begun to talk about is maybe there's a way to try and incorporate some of this physics that I've been looking at with these overstretched thin current sheets and try and place them in our MHD simulations to get a better match, both with the data mining reconstruction, but also with in situ observations. Okay, so just to conclude, we have this new PIC equilibrium for thin current sheets. It's stable. The current sheet does indeed overstretch the magnetic field. And crucially, we need this weak ion anisotropy to get our thin current sheet. And it just so happens that not only is it anisotropic, but it's also agyrotropic. This substantially modifies the force balance. I mean, as I showed, just as a reminder, 40% of our J cross B force is basically coming from this anisotropic ions, which are generated primarily by these Spicer orbiting ions, in particular the meandering ions. And because it's the Spicer ions that are responsible for this, it gives a natural explanation for why these thin current sheets are ion scale. One of the issues with trying to make the electrons responsible for these thin current sheets is there's no clear explanation for why electrons would give you ion scale thicknesses like a Larmor radius or so. But if it's the Spicer ions that are responsible, well, the width of their orbit is effectively the ion Larmor radius, and so it gives you this natural explanation. We've begun looking at these thin current sheets reconnecting while forcing them, and it looks like that is preceded by this ion watershed region, but also by including this BZ hump. And so there is a hope that this BZ hump instability is still unstable in these thin current sheets, but we haven't tried that without forcing yet. So that's something to do in the future. And finally, I just want to end with this question here. Okay, fine. If anisotropic ions are responsible for these thin current sheets, that's great. But where does the ion anisotropy come from? And it's not totally clear where it comes from. It could come from reconnection further in the tail. I've spoken to some people. Maybe it's from ionospheric outflow. Maybe it's just a natural side effect of thinning the current sheet. But this is a big question that I would love to know the answer to. So that's my talk. Misha and I do have a paper out on this from earlier this year. Yeah, thank you very much.
All right, thanks, Harry, for a wonderful talk. So there's a bit of a conversation happening in the chat between Joachim and Misha. Joachim did answer a couple of questions or ask a couple of questions, and Misha has answered them. But I will read Joachim's questions anyway so that you can see them. There are 5 or 6 parameters that go into your data mining approach. Can you identify which of these or which combination of them are responsible for determining the location of a thin current sheet or X line?
That is a really interesting question. I'm sure Misha probably has a better answer than I do, but I don't think it's been looked at specifically, but it wouldn't surprise me if it depends on, sort of the state of the magnetosphere, or really, I guess what I'm saying is, for a given storm, maybe some of these parameters are more important than others, but I don't know that it would be the same 1 or 2 important, for X-line generation. But maybe that's not quite right. The one thing that I will say, though, is that, SIMH or SMR is really the storm time index, and AL or SML is the substorm index. So I would think, at least in that sense, for substorms, the AL index is going to be more important, and similarly for storms.
Yeah, Misha goes on to mention that there's a overstretching factor, delta_2, that may contribute to this. And Joachim follows up with what determines where in X this becomes relevant. And then Misha finishes with that you guys are still trying to figure that part out.
Yeah, absolutely. I mean, it's a great question, but Misha's right. It's not, we don't have the answers right now, although we are looking into it. And delta 2 certainly plays a big role because it controls how embedded the thin current sheet is into your thicker current sheet. So yeah.
May I just a brief follow-up? I forgot the thin current sheet that is embedded in your model. Is the location of that free parameter, or is that a fixed parameter?
So I should say, okay, in the PIC simulations or the data mining reconstruction?
No, in the data mining.
In the data mining, Misha would be better able to answer that, but I believe that the location of the thin current sheet is something that is determined in the fitting process. So, once you have your 30,000 magnetometer measurements, you fit the magnetic field model And out of that pops the details of your thin current sheet. Misha, you can unmute yourself and correct me if I got that wrong.
Yeah. Joachim, do you hear me? Joachim, I wanted just to mention that in our reconstructions, we use very flexible architecture for the magnetic field. In particular, we assume completely independent distributions of thick and thin current sheets in the equatorial plane. So what you can see here, for example, in Harris' plot, in the growth phase, you have very long and overstretched, by the way, thin current sheets. As you can see, its sizer contours do not match magnetic field lines. And later, in the late expansion phase, it just disappears. So they behave completely independently, largely driven by data. And if you remember this, the whole idea, I mean, I should I should apologize. Harry is too young even to remember this story of thin current sheets. It started about 50 years ago with works of many of the colleagues, which some of you may know very well, like Tom Hill, Vitenis Vasilunas, Dick Wolf, and others. So I was surprised to learn that we're sort of trying to invent a wheel here, but really these problems are so pressing. In particular, without these overstretching things, we can hardly explain the formation of X lines beyond 20 RE when they are observed. So, but as I said, but coming back to these reconstructions, they are pretty independent. They just show what they show. And there are very few, perhaps the only parameter which is relatively weakly constrained in these reconstructions is the thickness of the thin current sheet. It is data derived, it is, but usually it converges relatively slowly. Other parameters are just driven from data very, very quickly. Did I answer your question,
Yeah.
Joachim?
Yeah, okay, to some extent, I thought maybe it was possible to play around with your model rather than applying it to particular cases and see how you can move the current sheet back and forth and see what determines
This
that.
is what we are
There's
trying to
something
play now with
external.
Harry.
Yeah. Mhm.
I'd say one of the most interesting experiments which Harry actually leading now is just to take the MHD model, which John Lyon, Karim, and others created, Gamera, and add the thin current sheet to there. See what happens with MHD. I think it's particularly interesting and intriguing what this thin current sheet we believe is a completely non-MHD feature. If it is not MHD, it should somehow change, modify the MHD configurations and even MHD evolution. It's very interesting to track. By the way, I think Dick Kaufman tried to do that, but he made it only with some empirical reconstructions again. I agree with you, yeah.
Okay, yeah, let's keep investigating that. Thank you.
So we have a couple follow-on questions. Zenon is wondering if waves play a role in your simulations and in the formation of the current sheet or the onset of reconnection.
I wouldn't. Well, I mean, in some sense, I suppose yeah, here we go. So you apply the electric field at the boundary, and that's going to end up squeezing your current sheet and penetrating the X line. That may be a wave of some sort. Certainly, PIC simulations have the capabilities of including all these other all various kinds of waves, but I guess I don't think about it typically in those terms. And since this is pretty much the whole simulation box, there's no interaction with, say, a lot of waves that are observed in the inner magnetosphere or ionosphere, that's not really coming into play in these simulations.
Okay. And then Elizaveta is wondering if there is a way to include plasma sheet turbulence in your models.
Well, let's see. So,
Harry,
you
this
know,
is exactly what we are planning to do. Take MHD, add thin current sheet, and see a whole bunch of turbulence.
yes, that is certainly true. I would also add that, you know, just looking at the PIC simulations, the inclusion of the third dimension, that out of plane dimension, so taking these from 2D simulations to 3D simulations will include a lot more plasma turbulence in the PIC simulations. And then, of course, Misha's right, you know, when you include thin current sheets in MHD, and of course, we're still trying to figure out how to do that properly, but that will, then you'll have all kinds of MHD turbulence playing a role and interacting with the thin current sheet as well.
Cool. Well, thank you again, Harry, and thank you, Misha and Joachim, for the interesting discussion. Our next seminar will be next week, and Harry Arnold will be talking about Aaron Ridley will be talking about the recently selected MAX small Explorer mission that's been selected for Phase A. After that, we'll be taking a little bit of a break for AGU as well as Christmas. So I hope to see everyone next week. And if not, have a safe travels for AGU and have a wonderful winter break. Thank you, everyone.
Thank you.